Hello, and welcome back to a video on MAT 1033 Intermediate Algebra. This is video number 44 in the series on the square root property. So let's return first to the function f of x is equal to x squared. We saw before that this function's complete inverse is a little bit tricky. It may not itself be a function. Now, if we only have a positive number, then truly the square root of its square is that number again. 2 squared is 4, and the square root of 4 is 2. In this sense, the square and the square root cancel. However, this is only half the story, because what if we just have the equation x squared is equal to 4? 2 squared is equal to 4, but also minus 2 squared is equal to 4. And so just taking the square root of both sides wouldn't give us both answers here. So in the sense that what we've used inverses for before is to solve equations, we really want something where we take both sides, do something to them, and get both answers. We saw this when we looked at inverses of functions, and we also saw this when we looked at radicals and square roots in the last section, but we also saw this when we looked at complex numbers. We invented, or perhaps discovered, complex numbers as being the solutions to x squared is equal to minus 1. And we said, all right, then we're going to take I, a made-up thing, or perhaps aren't they all made-up things, as being the square root of negative 1. The thing which, if I square it, gives me minus 1. But we also noted that its negative, or its complex conjugate, is equal to minus 1 when you square it. So we missed sort of one of the solutions. There was I, truly, by design, but also negative I came along as one of the solutions. Again, we missed a negative solution. Even when we made up the answer to our equation, it still seemed to have some kind of a gap going on here where we didn't necessarily detect. We had to kind of discover another solution that could have worked. In fact, there's only one time where x squared equal to some constant c has one solution, and that's when c is equal to 0. Because, of course, x squared is x times x, and the zero product property would tell you that x equals 0 here is the only solution you could get. Let's see one more reason why maybe there's more to the story and how we can patch this whole thing together by looking at the graph of x squared versus the square root of x, the principal square root of x. Well, we notice that they have sort of a reflective symmetry in this first quadrant, but there's something missing involving that negative branch. The full inverse of a function is its reflection over the y equals x diagonal. But if I take a look, there's nothing down there. I sort of have to fill this in. And if I fill this in, copying this branch and reflecting it down here, I get the negative of the square root of x as the other branch, which corresponds to negative x when you take its square. So this branch of the square gets reflected down to this negative branch of this sort of sideways parabola. Now, all of these things, all of these examples that we've seen have pointed us in the direction of what should be the full inverse, the complete inverse of x squared. It should be both. It should be this entire sideways parabola, even though it's not really a function, right? Because it fails the vertical line test. One value is actually sent to two different values if we consider both the green and yellow lines here as being our graph. And we sometimes write both of those things together as plus and minus the square root of x. So we sort of give this guy the plus sign. It's hidden out front, invisible, times plus 1 here. And this is minus that. So we write those two numbers together. This symbol always stands for two values, a plus 1 and a minus 1, square roots of x. Again, it's not a function because it gives us two values for each x. It's a relation, but it's a very useful one because we can use this relation to solve equations with isolated square terms. For example, if I have x squared equal to 4, then x squared must be plus and minus the square root of 4. That is to say, 2 and negative 2. Okay, critical notes. Copy this down, show it to me later, prove you watched the video. If I have something squared is equal to a constant, then that thing is equal to plus and minus the square root of that constant. This works for positives, negatives, 0, etc., all of them, right? This is the square root property. So even for 0, because the square root of 0 is 0 and plus and minus 0 is 0, this works. Also for negatives, because you can just factor an I out of the square root if it's a negative argument of the square root, and then you have plus and minus I radical whatever positive number is left inside. So the conjugate as well is a root here, just like we saw before. Now the main stipulation is that the squared term must be isolated. You have to have your x's be gathered together on one side, and they and anything else that's next to the x's have to be being squared, and there's no other x terms, right? We want all of our x's together, and we want the squared term. What we can't have, for example, is x squareds on one side and x's on the other, because you haven't gathered together the x's and sort of isolated the radical isolated the square as being one particular thing. Here, let's look at some examples. It'll be easier to see. These squares are isolated because it's just x on this side squared. This square is isolated. There's no other x's to worry about, and the only term on this side is squared. Everything else is sort of happening inside the parentheses, and then being squared. Over here, it's not isolated because this side isn't entirely squared. It's x squared, but then there's also a 3x. Here again, we don't have isolation. We have x's split between the two sides. This is x minus 2 squared. It's kind of not, that's right, but we didn't trap the 4x inside with it. It's out here. It's not isolated. It's not combined with the square term. So taking the square root plus and minus of both sides wouldn't really help you, because now you're just going to have an x under the radical and you're no closer to solving. So in order to apply this property, you need to have your square term isolated together, like one of these two. So what do you do if it's not? Well, you have to isolate it if possible, right? So what we're going to do here is isolate this squared term. Here we have a squared term, 3x plus 4 is being squared. We want to narrow our vision down on that bit and get rid of everything else on that side. Notice this stuff needs to go, the minus 2 and the times a fourth. If I add 2 and then I times by 4 to get rid of the fourth, now we are able to apply the square root property. Once we have the 3x plus 4 squared isolated, notice there's no x's over here, we square root both sides and we take the plus and minus of this square root. Now, that actually gives us two equations. We should break these apart and solve them separately, because this actually says 3x plus 4 equals 6 and 3x plus 4 equals minus 6. So we break those into two. 3x plus 4 equals 6 and 3x plus 4 equals minus 6, and then we solve those the usual way. That gives us 2/3 and negative 10/3 respectively. And so our answers are 2/3 and negative 10/3. Time for some practice exercises. Here's some things for you to solve. I want you to try solving these using the square root property. So pause the video at this time and give each one of these a shot. Okay, let's see how you did. So x squared minus 1 isn't yet isolated. We have to add 1 over to this side, and then we have x squared equals 25. From there, we can take plus and minus the square root of 25 to find the answers 5 and negative 5. Here again, we are not isolated. The first move is to isolate that square by getting rid of the minus 1. Once we do, we get negative 9 on this side, and taking plus and minus the square root of that, pulling our negative sign out as an I, we get 3i and minus 3i. Here we do have isolation, so we can proceed from here. We take plus and minus the square root of each side. So then to solve for x, we just get rid of the 1 by subtracting 1 from each side. This is the correct answer, although we could also reduce. Remember, square root of 12 is the square root of 4 times 3, so we can pull out a 2 from each one of these and write this as 1 minus 1 plus 2 square roots of 3 and minus 1 minus 2 square roots of 3. Here's a little one with a little bit more work to isolate the square, but just like before, we're going to get rid of this 2. Then we're going to divide by 2 on both sides to get rid of the times 2. Once we do that, we have an isolated square. We take the square root of both sides, plus and minus, and splitting these into the two equations, one for a positive 4 and one for a negative 4, we solve the usual way. This gives us x is equal to 0 or x is equal to minus 4, respectively. So those are our two answers. That's it for the main video. Here's some supplementary notes if you're interested. So this is going to be a method of factoring and also solving polynomial equations, quadratic polynomial equations, that will be focused on more in the next course, college algebra. But for right now, I just want to provide it as a bit of supplemental notes for the interested parties, because it's going to be used to produce one of the greatest tools that we have in our arsenal for dealing with polynomials, the quadratic equation. So in order to motivate that, I'd like to provide here an example of the method called completing the square, because really it starts to look like the square root property really can't help us for general trinomials. We can't isolate the square, we can usually just generally factor. And that's not the same, right? We need a square term to pop out, and it has to be isolated. So when can we really use this? Well, it turns out we can always use it for general trinomials, but we have to be a little bit crafty. We have to sort of set up a perfect square. The trick is going to be to manipulate the equation so that part of it looks like a perfect square. So remember that if we FOIL something out that looks like x plus b squared, what we get is x squared plus 2bx plus b squared. And so what we're looking at here is this middle term 2b. Let's make a substitution to make that part easier to look at. Let's say 2b is equal to c. Okay, well, if 2b is equal to c, then b is equal to c over 2. You'll see why I'm going to do this in a moment, but for right now, notice that I could replace the middle term with a c. But then I want to know what I'd need to do with these other components, the b squared and the b here. Well, the b is going to be half of c. And the b squared, if we expand out c over 2 squared, what we get for that, if we square b, is c squared over 4. Or if you like, that's x plus c over 2 squared gives us x squared plus c x plus c over 2 squared. So in order to have a perfect square, we need the squared term on the end, the constant term, to be half of the middle term squared. That's what we did this substitution for. Because take a look, the middle term is c. What's the last term gotta be? If we want it to factor this way, it's gotta be half of that squared. So now let's say we started with something that looked like x plus cx, x squared plus cx. Well, actually, we can make it into a perfect square if we add c over 2 squared next to it. And we're always allowed to do that, but what we need to do is sort of get rid of it in the same breath. We add it and we subtract it at the same time. And why is that so useful? Well, because now this part, the part in purple here, turns into x plus c over 2 squared. And the last part is just a constant. We're going to be able to get rid of this and isolate this square. This is going to work for anything that looks like x squared plus cx. We could move that over to the other side and say, move the c over 2 squared over to the other side and say that every x squared plus cx is actually equal to x plus c over 2 squared minus c over 2 squared. This is a neat trick because we're going to be able to take anything that looks like this and turn it into a square that we can actually isolate. We've got something here that looks like a perfect square. It's just got this extra side number, c over 2 squared, which we could calculate. Let's see what this really looks like with an example. Let's say I had x squared plus 6x plus 2. By the way, this one does not factor, so don't even try. What could we do to find out the solutions to this equation? Well, first off, let's move this 2 over so we can focus on the x squared plus 6x. Now, x squared plus 6x, that 6 is the focus of this method. That's our middle term. We want to take half of that, we want to square it, and we want to add that number, 9, to both sides. Half of 6 is 3, 3 squared is 9. And if I add 9 here, what I get on one side is a perfect square, in this case, x plus 3 squared. And on the other side, I've just got a number. So I've isolated my square. Using the square root property, I have x plus 3 is equal to plus and minus radical 7. And moving my 3 over, I get my two answers. X plus 3 plus radical 7 and 3 minus radical 7. Those are about negative 5.6 and negative 0.3 respectively. So we wouldn't have been able to factor. The zeros are not decimal, are not whole numbers here. But we could find out what they are exactly by using this method. In fact, we're going to see how this works for any square trinomial. Really, any square trinomial, right? Any quadratic trinomial, we're going to be able to write it in this form: ax squared plus bx plus c. And we'll see in the next video that we can get an answer to this equation, always, even if it's prime. even if it doesn't factor, even if we just use this kind of completing the square method. But we usually don't. We usually will take the fruit of that labor and produce something like an equation that will give us the answers to this equation just by plugging in the values of a, b, and c, the so-called quadratic equation. That's the topic for the next video, though. In the meantime, that's it for this one. Thank you for your patience. Have a great day and good luck with your studies. I'll see you in the next one.